and the basic information about the robotics were introduced in the last class, and the development of robotics and the various nomenclatures related to robotics we discussed in the last class. And we have introduced some joints and parts in the last class, and today's presentation we will discuss about the joints. If it is feasible, we extend the lecture into parts and links. And in the today's class, we will see some interesting videos related to the types of robots and the envelopes of robots. And with that, the today's class, and we'll start with various joints. And so we have given some insight towards various types of joints. And today we'll discuss a little more about the joints. Yes, this is what we have seen in the last class. Yes, Ajay, it is visible, Ajay?
Yes, sir, it's visible, sir.
Yes, types of manipulated joints. This is what we have seen in the last class. That is, we have 5 different types of joints. One is linear. The first 2 types of joints are called as translational motion. We have, that is translation motion. We have only translation. That is up and down or linear type of motions are categorized in translation. And with that, we have 2 different types of joints. One is linear joint. The other one is orthogonal joint. With the we will reveal various joints and various motion related to joints. The other one is other broad classification is rotary motion. One is rotational, twisting, and revolving. Please remember this notation. With that notation, we are going to call, or we are going to write the address on the, and so please make a note and make a hint of this various types of joint. I think you have deputed one separate note for robotics. I think so. If no one, if none of you have not dedicated to put a note, I request you to allot a separate notebook for the subject industrial robotics, and please make a note the content which we are disseminating through class, and therefore so that you can remind the things which during your examination, and for future reference it would be very easy for recollect the things. And I request you to put a separate notebook for the subject industrial robotics. And with that, this is linear type of joint, and it was written in short form in L. And this permits linear sliding motion between 2 links, and whose axes are parallel. See, whose axes are parallel, and which permits linear sliding motion, and that type of joints are said to be a linear joint. And the second joint is orthogonal joint. Here also we have linear sliding type, but the 2 links are perpendicular. 2 links are perpendicular to each other, but the motion between them, the joint is linear. And this is between linear type of joint and the orthogonal type of joint. And the orthogonal joint are written in O in the short form. And concerning the rotary motion joint, we have 3 different types or classification. The first one is rotational joint, and the rotational joint is written in R in short form, and it provides rotational motion of the joint with axis of the rotation perpendicular to the axis of the 2 links. See, with example we will reveal here. See, we have the rotation here. There is a possibility of the movement in this direction. Here, but concerning the axis of the 2 joints, here see the axes are coinciding, but the rotation is possible in this way. There is a possibility of the rotation. Therefore, this type of joint are written in short form, and it is called as rotational joint. Once again, I am repeating, it provides It's rotational motion of the joint with perpendicular to the axis of two links. Yes, yes,
Sir,
yes. Tell me.
sir, I think there's some problem in your voice, sir.
Yes, wait. I'll will.
Yes, now check with the audio, dear gentlemen.
Now
Yes,
it's
sir, now
fine.
it's fine.
Now it is fine. Okay. Yes, and concerning the twisting type of joint, and it also permits rotary motion. With these three provides or permits rotary motion. But concerning the twisting type of joint, the motion between two links are possible, but the axis of the rotation being parallel. Here the axis of input link and output link are parallel, then this type of joint are categorized into twisting joint. And the last under rotary motion joint is revolving joint, and this also provides a rotary motion, but the axis of the input link is parallel to the axis of the rotation of the joint, and the axis of the output link is perpendicular to the axis of the rotation. See here the axis of the input, we have the axis of the input link here and the axis of the output link here. Therefore, when the axis of the input link is perpendicular or normal to the axis of the output link and we have the motion, then that type of joint is categorized as revolving joint, and it is written in short form is V. So please remember this notations L, O, R, T and V. L denotes linear joint and O denotes orthogonal joint, R rotational joint, T twisting joint and V is revolving joint. And please remember L, O, R, T and V. And this is what we have seen, and with this slides we will move ahead. Polar coordinate body and arm assembly. Here the entire setup has the notation is T and R. There is a possibility of linear motion at the top, and here we have the axes are coinciding, but the rotation is possible in this way. Therefore we need to term it as R, that is rotational joint. Therefore the total notation for the setup is T and R. Here there is a description, that is it consists of a sliding arm that is actuated relative to the body, which can rotate about both the vertical axis, that is T joint, and horizontal axis, that is R joint. Therefore this type of joint is termed as TR, that is polar coordinate body and arm assembly. And concerning the cylindrical body and arm assembly, we have, see here there is a possibility here, this structure can move in the column in the rotary way. Is it so? Therefore here there is a possibility of rotary motion, and that too with the two axis of rotation being or parallel. Therefore it is said to be in T, and see here T, and there is an up and down motion is also possible in the column, vertical column. We need to term it as L, and here also there is a possibility of movement in the that is in and out or possible. Therefore here we need to term it as O, and see what was the difference between the L and O. Here the to and fro motion is up and down is possible, but in the case of concerning the O, here the two links are perpendicular to each other, but the motion between them are linear. Therefore it is termed as O. So the entire setup we need to call it as T. With a base we need to start, we need to give nomenclature, we need to assign the address with the base. Therefore, we need to call it as TLO. Therefore, we need to, the notation for this particular system is TL and O. It consists of a vertical column related to which can arm assembly is moved up or down. The arm can be moved in or out related to a column. Therefore, it is said to be an TLO and cylindrical body and arm assembly. And this is what Cartesian coordinate body and arm assembly. Here L, O and O. L, O and O. Three sliding joints, two which are orthogonal. And one we have in the column. Therefore, it is notated as L and O. Cartesian coordinate body and arm assembly. Concerning this joint, this is jointed arm assembly. Here there is in rotary motion possible. Here we have T, that is twisting motion. There are two different colors given in the weight, and there is a possibility of twisting here, and that is not clear with the picture. Here see this blue color, there is a possibility of motion in this direction. Here it was given. This is the way there is an rotary motion, and it was given in the axis. That is termed as, that is noted as T. This is one. We need to start assigning or giving the address from the base as twisting joint. Therefore, we need to start with the T. Then very nearer to the base we have, there is a motion called rotational joint. The rotational motion is possible. Therefore, we need to term it as R. Here also rotary, that is rotational motion is possible. Therefore, it should be notated as T, R and R. This is the general configuration of the human arm, and this is what the SCARA robot. And we need to discuss more about SCARA robot. Once we are very familiar with these notations, we will discuss a lot about SCARA robot. Here we have a column, and see there is a confusion between V and R. Here why we need to call it as V, and here why we need to call it as R. And someone please unmute your mic and tell me why this column tends to be V and this joint tends to R. In what way, how we have notated this into V and we have this into R? Please go ahead. Please someone unmute your mic and tell me how this should be V and this would be R.
So vertical, I think.
Yes, go ahead.
V is vertical and R is rotatory.
Pardon?
V is vertical and R is rotatory.
V is vertical
and R is rotation. Rotatory.
And here also we have the same type of motion. Is it so?
Sir, but is it? It is hinged to a vertical thing. That's why.
Do you think it is the right definition?
Maybe
Someone, please make a detailed note. Whether it is.
So the axis to which it is hinged is vertical, and for the other one, the axis to which it is hinged is rotatory. That's right.
Yes. Here the axis of the input link is parallel to the axis of the rotation of the joint. In the case of revolving joint, the axis of the input link is parallel to the axis of the rotation of joint, and the axis of the output link is perpendicular. Here see the axis of this joint is perpendicular to the axis of this joint. But in the case of here concerning this two case, axes are coinciding. Therefore, this should be termed as V and this should be termed as V. Okay. And this is called revolving, and concerning this one is rotational joint. and we need to start with base V, R, and O. O we are well aware that is the orthogonal joint, and that is two links are perpendicular to each other. Then we need to term it as O. Therefore, this type of joint is notated as V, R, and O. And SCARA stands for Selective Compliant Assembly Robotum. This is what the SCARA robot, and we need to discuss a lot about SCARA robot. And wrist configuration, we need to before that we need to watch some videos, and once you are very familiar with this content, that is L, O, R and T and V, then we will move to wrist configuration. And with that wrist configuration itself, we need to remember the roll, pitch and yaw and the degrees of freedom. And once we are very familiar with that, we'll discuss wrist configuration. We will see some videos related to the degrees of freedom and the types of robots. Yes, the audio is. Are you able to hear the audio? Video itself has some audio.
No, sir.
Are you able to? Are you able to hear the audio?
Sir, play the video, then we'll understand. No, sir, there is no audio.
And I have given. Now check.
No, sir. You need to share audio as well, sir.
Yes, tell me.
You need to share audio as well, I guess.
I have shared.
Audio as well, not video alone or presentation alone.
Someone you have Sabarni?
Yes, sir.
You have shared the content
Sir, which content?
related to making the audios and
Yes,
all.
sir. Yes, sir. I have shared that you can open your WhatsApp and check.
Yes. Yes, this is the way I did it, but why?
Sir, like, can you try it again, maybe then?
This is the way I have turned on my audio also.
Stop the presentation, sir, and try to reshare the presentation, and there will be an audio sharing option, I guess.
Yes, yes.
arm geometry.
Now check with audio.
Use Cartesian.
Yes, it's working.
Yes, sir.
Yes.
It's fine.
Yes, thank you. And this is what the arm geometry. And please remember the notations, the various notation which is allotted for the joint. Please remember L, O, R, and T and P. And please see the video.
There are four main types of robotic arm geometry: rectangular, cylindrical, spherical, and jointed spherical. Robots with rectangular arm geometry use Cartesian coordinates and move linearly along each of the X, Y, and Z axes. This type of movement is also called 3P geometry, where the P stands for prismatic or linear motion.
That prismatic, please someone remember what is prismatic? Prismatic, we have already talked about the pairs, and we have introduced 5 different types of pairs. Once I'll it is audible. My audio.
Yes,
Yes,
audible.
Yes,
yes,
sir.
I have given 5 different types of pairs. One is revolute pair, prismatic pair, cylindrical pair, spherical pair, and hook joint. And concerning revolute pair, that has to be written as R. It has 1 degree of freedom. The prismatic pair has we need to term it as P, and that also has 1 degree of freedom. Concerning the cylindrical pair, that has to be written as C, and it has 2 degrees of freedom. And spherical pair has 3 degrees of freedom. The hook joint, I think I didn't talk about the hook joint. I'll tell you what it means, and it has 2 degrees of freedom. Concerning this prismatic pair, and it has 1 degree of freedom. And I'll remember these points which is related to other pair also. That is revolute pair permits relative motion about a unique pair axis and has single degrees of freedom. And concerning the prismatic pair, the relative sliding parallel with a unique pair. And cylindrical permits independent relative rotation about and relative sliding parallel to the path. And this is what we have given with some slides. And spherical also we have detailed, and therefore it has to be written as prismatic. And please remember this 3P with that pairs.
This type of geometry is most commonly used with pick-and-place or large overhead-mounted robots. Rectangular arm geometry robots can only move linearly in each direction. An overhead crane robot is a good example of this type of motion. It can move forward and backward, left and right, and up and down. Robotic arms that use Cartesian coordinate geometry generate a rectangular work envelope.
Yes. The work envelope, there is a possibility of covering some certain space or volume is said to be an work envelope. The arm has a flexibility. The largest amount of space or volume covered by the arm is said to be an envelope. That is usually said to be an work envelope. Therefore, concerning this type of rectangular arm geometry, and it has rectangular work envelope.
Rectangular robotic arms have the simplest geometry and control system and are typically used in material handling operations. Cylindrical arm geometry robots move linearly in 2 directions.
This is second type of geometry, that is cylindrical arm geometry,
And rotate in one other. Since this type of robotic arm moves in 2 separate prismatic or linear directions and rotates in one direction, it's given the designation of R2P, where the R stands for rotational. This type of
R2P. Please remember R2P.
robotic arm is most often used in machine tending, assembly, material handling, and palletizing operations.
Do you know that what is meant by palletizing? What is palletizing?
Hello.
Please
Arranging
go.
in pallets.
Converting, making the powders into some tablets. Converting powders into recumbent shape is nothing but palletizing. Yes.
Robotic arms with cylindrical geometry move linearly in two directions. Vertical linear motion is called stroke.
Yes, please remember this also. The motion, we need to remember these motions, and this linear motion should be called as a stroke. Please remember this also.
Horizontal linear motion is called reach.
Reach.
And rotational motion is called swing.
Swing. And there are three different types of motion, and one is stroke and reach and swing. Stroke, reach and swing. The up and down motion, we need to call it as
Cylindrical geometry robots have a cylindrical work envelope. The advantages of this type of work envelope is a robotic arm reach that is deep at both the top and bottom of the stroke.
Yes, it is cylindrical work envelope. And concerning the largest possible dimension and the shortest possible dimension, in both way we are getting a cylindrical work envelope. And this is the largest, the outer cylinder is the largest possible way, and this cylinder, inside cylinder, is in shortest possible way we are getting. In both the way we are getting cylindrical work envelope.
Additionally, the robot structure allows for quick movements with high repeatability, a smaller use of floor space, and a larger payload capacity due to structural rigidity. Spherical arm geometry
This is the third geometry, that is spherical arm geometry.
Robots can rotate in two directions and move linearly in one, and thus are given the designation of 2RP. The robot has,
please remember, that is 2RP, polar coordinates, 2RP.
Base rotation, shoulder rotation, and prismatic or linear motion at
base, shoulder, and prismatic
the arm. This type of robotic arm is most often used in machine tending, material handling, welding, painting, coating, and assembly tasks. Robotic arms with spherical geometry have rotational movement in two directions, rotational movement at the base and rotational movement at the shoulder. Spherical arm geometry robots also have linear motion in one direction, typically the reach of the arm.
Reach, it has to be called as reach.
Spherical arm geometry robots have a mostly spherical work envelope at their outer reach, but are limited by the linear reach of the arm and the rotation of the shoulder joint. The shape of the robot's inner work envelope.
See this spherical oak envelope, spherical oak envelope, when it has an utmost reach, we have a spherical envelope. When it is, the reach is very, very minimal, and we have some cylindrical type of geometry, and this is what the spherical oak envelope of spherical arm geometry
is almost conical and does not become a sphere until the arm extends.
See?
Spherical arm geometry robots typically have a very long reach and have proven their performance in industrial applications. However, their high cost, large use of floor space, and lack of flexibility compared to jointed spherical arm robots make it hard to justify in most industrial applications. Jointed spherical.
This is the fourth geometry, that is jointed spherical arm geometry.
Arm geometry robots have rotation in three directions, use revolute coordinates, and are given the designation of 3R. They are one of the most popular types
3R, please remember the notations, 3R.
Of robotic arms and most accurately mimic the movement of the human arm. Robotic arm.
It mimics, or it copies how the human arm works, and it mimics the same in the way that how the human arms rotate and does it works.
arms with jointed spherical or articulated geometry rotate on at least 3 axes. Left and right movements are provided by rotation at the base. Horizontal movement is provided by rotation at the shoulder. And vertical movement is provided by rotation at the elbow. Except for very close to the body, the work envelope of a jointed spherical robotic arm is almost entirely spherical.
Although this also has the spherical work envelope.
The advantages of this type of work envelope is a robotic arm with very deep reach, minimal floor space use, and high positioning mobility of the tool end arm. Due to its mechanical complexity and the complexity of its controller, this robotic arm typically comes with a higher hardware cost and requires skilled technicians. Robot.
This is what the various system, and with that we need to aware about the various degrees of freedom. And please see the video.
Robots come in all different shapes and sizes, but are frequently classed by their degrees of freedom. Each direction of movement on the robot is considered an axis of movement. This robot rotates at the waist, bends forward and back at the shoulder, and moves vertically at the elbow. Each single movement axis is equal to 1 degree of freedom. This particular robot is equal to 6 degrees of freedom. It moves along one axis for each of the waist, shoulder, and elbow joints.
Waist and elbow, shoulder and elbow.
And along 3 axes at the wrist using pitch, roll, and yaw.
Pitch, roll, and yaw.
These particular motions help to locate the tool
shoulder,
in the work area
elbow,
and are called position axes. Most robots have at least 3 position axes to help position the tool in the work area. If the robot were to slide along a track, it would have a 4th position axis of linear movement and another degree of freedom.
Then therefore, when this movement, the robot arm moves in one rail or one track, that has to be considered 1 degree of freedom. That to and fro motion we need to account as only 1 degree of freedom. And we usually what we do we need to consider the to as to and fro, to as 1 and fro as 1. It won't be right, and it has only 1 degree of freedom. We need to consider that to and fro with 1 degree of freedom, and therefore the entire system has 6 degrees of freedom. Like what we do usually in mathematics, like in factorial, 1 into 2 into 3, that won't be right concerning the degrees of freedom. That we need to take it as 1 at one particular point, other at other particular point. Then we need to add this 2. Therefore, that should be called as 2 degrees of freedom.
While the position axes locate the tool in the work area, the orientation axes help orient the tool in relation to the workpiece. The types of movement along orientation axes are defined as pitch, roll, and yaw.
Pitch, roll, and yaw.
These movements all occur from the same joint, the wrist, but along 3 distinct axes. This type of movement is most easily illustrated as it relates to aircraft movement.
Yes, pitch. This is called pitch, and this is called roll, and this is called yaw. Pitch, roll, and yaw. Anyway, with some other video also I'll make a detailed note about this pitch, roll, and yaw. Once again I am showing. This is wait, pitch. This is called pitch. Pitch and roll and yaw.
The robot's tool moves in the same way. Pitch moves the tool vertically. Roll rotates the tool about its center axis. Yaw turns the tool left and right. The position rotates the tool vertically. The tool moves in the same way. Pitch moves the tool vertically. Roll rotates the tool about its center axis. Yaw turns the tool left and right. The position axes movement at the waist, shoulder, and elbow, along with the orientation axes movement of pitch, roll, and yaw, allow the robot to accomplish its tasks within the work envelope.
This video will tomorrow we'll discuss. Tomorrow we'll see some more detail about pitch, roll, and yaw, and we have other videos which details about various robots and all robot arm geometry. And I think you are very familiar with the robot classification. I think robot various joints and various arms and various geometries and various degrees of freedom related to the robot. And do you have any doubts with today's presentation?
No, sir. No, sir.
Yes,
No,
good.
sir.
So no doubts, just want to know when will you share these videos and the presentation?
Is as similar to that of the numerical methods class. Once
Okay.
we are completed unit 1, I'll share the PPT.
Okay, sir.
In the meantime, I will share the video links at all. Once I
Okay,
have
sir.
uploaded in our Google Classroom, I'll share the link.
Okay, sir. Thank you.
These are the videos which I have collected through Google, the search engine, that is Google. Anyway, we'll make it as into a single roof. You need to collect. Once I'll upload and I'll share the link also.
So it's available in SlideShare. I have seen it.
Yes. Yes, please remember the notations. Please remember the pairs and joints. With that, we are going to have the further discussions tomorrow. Therefore, I request you to remember the pair notation and the notation related to the joints. Okay.
Okay, sir.
Yes. Okay, thank you, Anurag. Thank you. We'll meet tomorrow at 11:20. Sorry, 11:30 we'll meet.